This is a demonstration of the pathline tracing features in an AXIM. We're going to trace flow paths around a pumping well to delineate the zone of contribution. And then we also want to find the area at land surface that contributes recharge that flows to the well. I want to start with a couple definitions. The zone of contribution is the three-dimensional zone in the aquifer within which groundwater flows to the pumping well. The area contributing recharge is the area at land surface, or actually at the water table, where recharge enters the aquifer to supply the well. The aerial extent of the zone of contribution is the 2D map area that encompasses both the area contributing recharge and the zone of contribution. This is sometimes also called the capture zone of the well. This is the basic setup of the AXIM model. The model is 25,000 feet long in the direction of flow and 10,000 feet wide. The regional aquifer is modeled as a single-layer, unconfined domain with recharge. Head on the western boundary is set at 300 feet. Head on the eastern boundary is set at 180, so groundwater flows from west to east. The model base elevation is 0, so the aquifer saturated thickness is about 200 to 250 feet over the main area of interest. Aquifer hydraulic conductivity is set to 20 feet per day, and the vertical anisotropy in the three-layer area around the well is 10 to 1, horizontal to vertical. Aquifer recharge is set at 9 inches per year, and the well is pumping at a constant rate of 15,000 cubic feet per day, or a little over 110,000 gallons per day. The cross-section view from west to east shows that the well is screened over a 30-foot interval in layer 2 of the model. This means that the well is partially penetrating, and the three-dimensional flow near the well will factor into the pathline tracing. The flow solution with the well pumping shows a water table that slopes from west to east. This means that the zone of contribution will be located up gradient west of the well. In this demonstration, we will trace pathlines backward from the pumping well to outline the horizontal extent of the zone of contribution. We will also trace pathlines forward from a point location and from multiple points along a line to fill in the picture of the 3D zone of contribution. Finally, we will start pathlines over a large area of the water table up gradient from the well and trace them forward toward the well. By outlining the starting area of those pathlines that are captured by the well, we can find the area contributing recharge to the well. We will begin by starting pathlines around the well and tracing them in an up-gradient direction. This will provide a first look at the horizontal extent of the zone of contribution of groundwater flowing to and being captured by the well. Here is what that looks like in the AXIM input data grid. We select from the menu Plot Input, Pathlines, Well. We tell AXIM to start pathlines around Well 1, the name of the pumping well in the model. In this model, with flow directly east, I deliberately specified 11 pathlines. The odd number starts one pathline exactly on the downgradient side of the well in the direction of the stagnation point. This helps in depicting flow in that area. And as I mentioned, we specify the starting level as 2.5 to start the pathlines at the vertical midpoint of the well screen in level 2 of the model. Pathlines traced from wells are automatically traced backward or up gradient, so we won't have to specify that. The pathlines traced back from the well show the general area of the zone of contribution. In some cases, you might be tempted to just stop here and draw a polygon around this area. But we're going to perform additional pathline tracing to refine our depiction of this flow zone and, more importantly, to delineate the area of recharge that is supplying water to the well. Here is what those pathlines look like in cross-section. We can see that groundwater recharge starts at an area up gradient from the well, but we will need to fill in the flow patterns in the shallow zone near the river and in the deeper zone beneath the well to better delineate the full extent of the zone of contribution and the area contributing recharge. To do that, we will start a stack of pathlines from the water table to the bottom of the aquifer at a point located far west of the pumping well. We will also start a group of pathlines along a line at the water table in the area just up gradient from the river. Here's what that looks like in the Anaxim data entry grids. For the single pathline starting location, that is the single point, we specify a starting location up gradient from the well at x equals 1000, y equals 4100. We tell Anaxim to trace pathlines downstream from starting locations at depths ranging from the water table at 1.0 to near the bottom of the aquifer at 1.95. The values are separated by commas. Next, we specify a line of pathline locations that extends from starting XY location 9,049.50 to the endpoint 17,049.50. We tell Anaxim to distribute 9 pathline starting locations along that line and to trace them downstream in the aquifer starting at level 1.0, which is the water table. The additional pathlines really help to fill in the picture of the flow field. Shallow flow up gradient from the river rises and discharges into the river. It's not captured by the well. Mid-level flow rises toward the river, does not reach the river, then dives again slightly due to recharge from above, and then finally enters the well. Deep flow is drawn upward into the well, and very deep flow underflows the well. It's not captured by the well and flows off to the east. This gives us a general extent of the location of the area contributing recharge at the water table up gradient from the well, but we realize that we have not determined its footprint over the land surface. We can do that using one of Anaxim's advanced features for pathline tracing, area pathline arrays. We first digitize a polygon area over the surface of the model within which we want to start a swarm of pathlines at the water table, where recharge enters the aquifer. We specify the pathline spacing within the polygon, 150 feet in this example, and Anaxim calculates the necessary starting locations. This results in the creation of 671 pathline starting locations in this example. Then we trace all of those pathlines forward and keep track of which ones are captured by the well and which ones are not. The area covered by those pathlines that are captured by the well represents the area contributing recharge to the pumping well. This gives a very good representation of the area contributing recharge, but more time is required to trace all of those pathlines, so be careful not to specify too large an area when you are doing this. To have Anaxim determine which pathlines are captured by the well, we turn on the Capture Constraint feature for pathline tracing, and we enter the well label Well 1 in the Capture Wells data entry cell. This tells Anaxim to display only those pathlines that end up getting captured by Well 1. This is the resulting constrained pathline display. The plot looks a little busy because Anaxim is plotting both the circle symbols at the starting locations and the pathlines that are traced from those symbols to the well. To delineate the area contributing recharge footprint, all we need to see is where those pathlines started at the water table. In other words, we only need to display the starting location symbols. To get the plot we want, we open the View Manager, locate the pathlines we used in this ACR analysis. They are labeled Anaxim Pathlines ACR, and we click on the Freeze button. This turns off not only the pathlines but also the time markers, the arrow symbol, associated with each pathline. That leaves only the start point symbols displayed. This is the plot we wanted. The group of starting pathlines at the water table that flow to the well delineates the footprint of the area contributing recharge to the well. If we draw the bounding polygon for those points, we define the ACR boundary. One quick check to see if this is a fairly accurate delineation is to multiply the recharge area by the recharge rate over that area. When we make that calculation, we get a value of about 15,100 cubic feet per day of recharge feeding flow to the well. This matches closely the specified discharge rate of the well of 15,000 cubic feet per day. One final thing I wanted to show you is a comparison between the area contributing recharge for this model and the ACR calculated for the same model with the river removed. You can see that the recharge area with no river capturing shallow groundwater flow is much narrower and covers the area directly upgradient from the well because the flow field is not distorted by the hydraulic effects of the river. This demonstrates the need in many instances to include important hydrologic features in your model when you are performing pathline tracing for various applications. For example, including partially penetrating well screens and groundwater discharge to rivers. And Anaxim has the capabilities that allow you to do that. This concludes the Anaxim pathline tracing demonstration.